Imagine you have the power to make smarter, data-driven decisions for your community. How would you allocate resources, monitor urban development, or predict economic trends? Today, we're going to explore 3 powerful tools in the world of artificial intelligence that can help you do just that: feed-forward neural networks, convolutional neural networks, and recurrent neural networks. Let's dive into each one using practical examples that could directly impact your role as policymakers. Part 1. Feed-forward neural network (FNN). Refer to the left side of the diagram. First, let's talk about the feed-forward neural network, or FNN. In an FNN, data flows in one direction, from the input layer, through hidden layers, and finally to the output layer. Think of it as a one-way street where information is processed without any loops or backtracking. Each input moves through the network layers, and the network produces an output based on the current data alone, without retaining any past information. FNNs are ideal for simple, one-time decisions where each input is independent of previous data. They are often used for classification and prediction tasks where we want a straightforward answer based on the current set of inputs. Now, think about a scenario where you're deciding how to allocate community resources. What factors might you consider? Maybe the population density in the area, the average income, or the availability of community services. Here's where the FNN shines. It takes these inputs, processes them, and gives you a recommendation, like fund a new park or open a new library. The network doesn't need to remember past decisions, it just processes the data you give it and offers a one-time suggestion. Part 2. Convolutional Neural Network (CNN). Now direct attention to the center of the diagram. Next, we have the convolutional neural network, or CNN. CNNs are designed to handle visual data, such as images, by recognizing patterns within them. They do this by breaking down images into smaller sections, which allows them to identify features like edges, textures, and shapes. You'll notice the layers labeled a convolution and a pooling. The convolutional layers extract features from the images, while the pooling layers reduce the data size, focusing on the most critical elements. After several rounds of convolution and pooling, we move to the flatten layer. This layer takes the 2D feature maps created by the previous layers and transforms them into a 1D vector. Think of it as unrolling a folded piece of paper. Now the network can process all the features as a single list. This step is essential because the next stage is the fully connected layer, which functions similarly to the FNN we discussed earlier. In the fully connected layer, each feature from the flattened vector is connected to every neuron in the layer, allowing the network to combine all the detected patterns and make a final decision. This fully connected layer is what ultimately produces the classification or prediction. CNNs excel at tasks involving spatial patterns and are commonly used in image recognition, object detection, and even facial recognition. They're incredibly useful whenever we need to analyze and interpret visual data. Let's consider a real-world application. Imagine your task is to monitor illegal deforestation with satellite images. The CNN would scan these images, just like your eyes might scan a photo for specific details. The convolutional layers detect features, like tree cover or bare land, and the pooling layers simplify the image, focusing only on what's important. Once the feature maps are flattened and pass through the fully connected layer, the network provides a classification: forest, cleared land, or urban area. Part 3. Recurrent Neural Network (RNN). Now shift to the right side of the diagram. Finally, we have the recurrent neural network, or RNN. RNNs are unique because they have loops in their hidden layers, which allow them to retain information from previous inputs. This means they are capable of remembering sequences and using past information to inform the current processing. In other words, RNNs are built for tasks where the order of the data matters, such as time series data or language processing. RNNs are well suited for tasks involving sequences or trends. They are often used in language translation, speech recognition, and any application that benefits from remembering prior inputs. Now, let's apply this to economic forecasting. Imagine you have quarterly data on GDP, inflation, and employment. With each new data point, the RNN recalls past trends, helping you predict future economic conditions, whether we'll see growth, stability, or possibly a recession. This continuous learning is exactly what we need for making informed predictions. In summary, each of these neural networks brings a unique strength to the table. Firstly, FNNs are best for straightforward decisions where each input is considered independently. They're great for one-off classifications and predictions based on the current data. If you need to make a quick, data-informed choice, the FNN is your ally. Moreover, CNNs excel at visual data analysis. They can recognize patterns in images, making them invaluable for any policy-related task that involves monitoring changes over time or enforcing regulations based on visual data. Finally, RNNs are ideal for tasks where the order of information matters. They're designed to understand sequences and help you make predictions based on past patterns, which is essential for planning and preparing for future challenges.